That sounds great. Justin, thank you so much for the intro, and Allison and the whole group for having me. Really excited to be here. I'll also say that I really wish I was in Minnesota right now because I'm in Philly and it's about 93 with an 80% humidity. So you can't even go outside. Yeah, it's pretty brutal. All that is to say, great to meet you guys. Let me share my screen and we will dive in. Justin, can you see my screen okay still? Excellent. Very good.
Great.
So yeah, Justin, thanks for the intro. As he mentioned, we're going to be talking. I'm really excited to share some of the work we've done with Chassis.ml, which is our completely open source project. There are a few edge specific, talking points I'm going to add a little bit later in the presentation, which is a little bit more specific to Modzy, but not exclusive, with Modzy. So I thought that it was a great way to kind of bring this to life, and especially as edge AI is becoming more and more prevalent. So the other thing I'll do before I forget, I'm going to share a link in the chat for the latest chassis site. Long story short, we're working through a issue with our domain registrar. So this is the backup URL we have, and you can kind of peruse that at your leisure as I go through this. So quick intro of myself. Again, as Justin mentioned, I'm at Modzy, machine learning engineering and pre and post sales engineering, work very closely with our customers. Really enjoy the dynamic day-to-day learning new use cases and all the different tools in this evolving space. Prior to Modzy, I was at a tech consultancy, worked with a variety of both federal government and commercial clients. So I have a lot of experience in the data science, machine learning engineering, in kind of AI space. A little fun fact, I am a big sports enthusiast and fan, so maybe we can sync up separately if that applies to any of you. So today I'm going to break up the talk into two components with a couple demos, dispersed throughout. The first, I'll just give a broad overview of Chassis, some of the motivation that we had to build this tool, some of the common challenges we both saw and continue to see that Chassis solves, in addition to some of the high-level concepts of the solution. I'll show you a demo, and then also in the second section, show a lot of real-life examples of Chassis containers in the real world. The idea of how does Chassis kind of power and be a foundation to a robust MLOps solution. Also, feel free to interrupt me, go on mute, ask any questions as you have them, or drop some questions in the chat. Okay, so as I frame the problem that Chassis solves, I really wanted to come at this from two angles. One, the set of common challenges that we saw and continue to see. And second, it would be a little bit more edge specific, two categories of problems that Chassis solves for. The first problem that we solve and challenge is, quite simply, data science is not anywhere close to DevOps. What I mean by that is the skill set and knowledge of data scientists is very different from that of DevOps professionals and experts, right? Data scientists have strong foundations in math and statistics and can build these powerful prediction models and deep learning models. And DevOps engineers and professionals specialize in shipping production software and container. And there's very little, if any, overlap, which creates a challenge when you're trying to operationalize machine learning. Another challenge, very simply, is that all models are different from in a lot of different ways. Input and output structure varies from model type, NLP versus computer vision versus tabular. When you interact with models, it will differ depending on the framework you use to train that model. Scikit-learn classifier, versus PyTorch versus TensorFlow, all very different. Plus a number of other factors that just make it tough to standardize the way that you consume and kind of represent models. And finally, production deployment environments can be highly variable. Sometimes you might want to deploy a model to a collection of different hardware types with different operating systems, and you want to make sure that you don't have to build bespoke deployment solutions or applications for every environment you're working in. So that's one angle of problems that Chassis aims to solve. The second is around this idea that edge is really the future of AI. The concept of bringing model inferencing from the cloud and on-prem directly to the edge where the data is collected. Some fun stats here that we like to talk about, estimated 43 billion connected devices at the edge by the end of this year. 75% of enterprise data will be created and collected at the edge by the end of 2025, 90% of which will be unused due to a variety of factors. So Edge AI enables a collection of benefits, namely, more real-time insights, faster time to value for the end consumers, lower cost. It costs a lot of money to send data from the edge to the cloud and process it there. And the benefits go on, which is why, at Modzy, we focused a lot on this. And our approach with Chassis makes it really easy to ship models, remotely to edge devices. We'll talk about that. So when you think about this very simply, on one hand, you've got a trained machine learning model that could come from any collection of tools you might be using, frameworks, things that throughout the community are very easy to use, accessible, and great for building models. And if you want to deploy that to some target edge or cloud devices, the devices might look very different. Cloud infrastructure is very different from a single board computer. I'm going to probably flash this little Intel upward I have several times throughout this talk. The infrastructure is different, the chipsets are different, and there's this natural chasm that's created that we need to fill a gap. And one way to think about that is to come up with a robust and effective model serving solution. There are lots of different ways to categorize and define model serving, but we like to break it out into 3 different components, those being packaging models, deploying models, and serving models. And when you look at each of those components separately, it becomes much more complex very quickly. We'll start with packaging models. Some of the considerations that I already discussed include what type of model are you working with, what programming language was used to develop that, what sort of frameworks we're using. When you think about production, do we want to add in a web server? Do you want to make it API accessible? What about pre-processing of data, post-processing, et cetera? And then once it's time to deploy that model, how are you going to customize the configuration of hardware resources that container may need to run? What about container runtimes, security? How do you want to add automation into your deployment system to customize and integrate into your own CI/CD pipeline? And then, on the serving side, are you going to build a custom Kubernetes service? Are you going to use an existing platform, or maybe open source or commercial? Does your solution need to be highly available? How are you going to handle downtime, failures of containers, things like that. So as you can see, it becomes very complex to figure out how you're going to create a solution and make sure that it's flexible, efficient, scalable, and takes into account all these considerations. Well, what we sought out to do is solve some of the problems I've discussed around the packaging component, specifically with Chassis, because we think that a sound packaging solution sets a strong foundation that allows you to be flexible and kind of build on top of that with deployment and serving. And they're all linked kind of interchangeably, but you'll see some examples of what I mean by that. So let's just break out this packaging box for a second and describe what the Chassis solution will do. So Chassis is a Python package. So for all of us who develop and build models in Python, it's really accessible, it's really easy to use, and you can download and use it right alongside your existing training code. As an example, let's say you're building a PyTorch model, you've got some sophisticated training code, Chassis could be a separate script or at the bottom of that code and allow you to convert any Python model into a production container without having to know anything about Docker, Kubernetes, web servers, APIs, et cetera. It automates all of that and abstracts those skill sets away from the data scientist persona. And so the output of a Chassis build job, as I mentioned, is a production container that exposes a gRPC API and allows you to pass through your own data through that API and get predictions out. And so this is powerful because then you've got a production container without having to know how it was built. And you've got a ton of deployment options when we're talking about deployment and serving. And you could deploy this model to a commercial product like Modzy as an example, or Kser, which is open source, or you could build your own Kubernetes serving platform, or you could run it locally with Docker. Some of those examples I'll show in a little bit. And then from the infrastructure level, that's kind of the serving level. from an infrastructure level, this container is completely agnostic of that end infrastructure. You could certainly deploy it to a cloud server or some on-prem data center, and even out to a small form edge device because of how we've built, the chassis construct. So generally speaking, high level, that's what chassis is. Let's switch gears a little bit and check it out. Okay, at the beginning of my talk, I pasted a link. And so for those who joined late, the link to the chassis site's at the top of the chat. Chassis.ml is our normal domain. We're working through an issue of getting that resolved. I'll just walk you through and kind of give you a quick tour of the site here. As I mentioned, it's really easy to get started. All you need to do is pip install the Chassis.ml package, bring your Python model, and have some credentials to a Docker registry. So what Chassis will actually do is it will, and I'll walk you through an example, it will serialize, build a container out of your model, and push that to some Docker registry. And so there are a few options there that we'll get into, but again, it's super, super easy to get started. I'll come back to this getting started guide, but just to highlight a couple of the other pages, that are available. It is a Kubernetes service, so you can Helm install the Helm chart, really easy to get started. You could use our publicly hosted service totally for free, and that's what I'll use today. It doesn't require you to set up any infrastructure. Alternatively, if you happen to be working with Kubernetes, you already have applications, you already have clusters that you manage, you could install Chassis right in that Kubernetes cluster and kind of manage your own instance separately. We've worked with organizations who have taken advantage of this, who are very sophisticated and have a lot of automation built into their kind of end-to-end MLOps, processes, and have taken advantage of that. So this guide will walk through that. Some how-to guides, some specific, model frameworks that you might be using. Of course, our API reference and some conceptual guides that just kind of gives a better understanding visually of what Chassis is. So feel free to play around with this and get some more of the information yourself if you're interested. For our getting started guide, as I mentioned, you start by just pip installing the package. We have a kind of a getting started notebook in the repo that we're pointing to, and I'll open up in a second. What I will just note is if you go back and check this out yourself, there are some annotations that I'd recommend you look into. If anything I say is confusing or doesn't make sense, everything's laid out very clearly here in this getting started guide. So enough of that. Let's actually see what a Chassis build job looks like. So I'm just going to go through this. I will start by importing the Chassis package in addition to any other model specific, libraries that I need to import. And then I actually trained a scikit-learn model. So I happen to follow this specific example where I just trained a super simple digits classifier, right? So it's a logistic regression, classified this or trained on this digits data set, and I saved it as a pickle file. So I've got my trained model that I'm just loading in with the pickle function. And so now I have an in-memory model. Important to note there, because the next step is to define something that I'll call a process function. You can maybe think of this as just an inference function that will take in some data, use in-memory models and other dependencies to process the data, format the data, and return the results. So if I go through this line by line, I'm first just reading in some raw bytes, converting it into a NumPy array, which is what my model expects, using the model predict function here, and then structuring the output into a dictionary that's easy to interpret and use for downstream tasks. Just to show you guys what we're working with here, here's an example image that I'll use throughout this demo of one of the digits images, and then Chassis will do the rest. So we'll start by instantiating our client, and I mentioned that there's a service running publicly hosted. You can use this. And so I've got my client established, and then I'll create a Chassis model object simply by passing through the process function that I defined. It's the only parameter. If you wanted to add more things here like batch processing or GPU support, you could do that as well. And then what I can do is actually test this model out. So I basically saved this image as an array and serialized it as JSON, loaded it in and passed it through to my model. And we see that it predicts this image being a 9-digit with 100% confidence. So super easy to test what my chassis model object will do on some sample data. Then, as I mentioned, I'm going to pass through some Docker Hub credentials for my personal Docker Hub account. You have the option to manually define an environment with some dependencies. So this model relies on scikit-learn, NumPy, and then Chassis.ml to ultimately run within that container. I'll define that. And then I'll just simply publish my model. So let's see here, make sure I didn't mess anything up. That looks good. So when I publish my model, I'll pass through a model name, a model version, and some credentials, and then my environment. What Chassis is doing, the service is doing, is it's taking my chassis model object, it is serializing it, and it's taking some of the dependencies that I defined, and it's building a container out of it. Now, this will take anywhere from 3 to 5 minutes or so. So I went ahead and ran this ahead of time. And what the output looks like is simply a container in my Docker Hub account. So again, in just a few minutes, version 002 should be complete, and I'll show you what that looks like. But in the meantime, I pre-ran this ahead of time, and now I have a production container, right? For those who work with Python know that after you train a model, you've got to set up your virtual environments with the specific dependencies and version of Python, and to run that code can be cumbersome. And when you think about replicating that in a variety of infrastructure, production systems, and environments, it can be a little bit overwhelming. But by containerizing it, we're creating an immutable asset with everything in there that we know will run, and it will work anywhere. And so I could download this myself. My team could download this. They could, and there's a kind of a lot of downstream applications that we can use this for as it pertains to deployment and serving. So let me switch screens again to my terminal here. And I'm going to just simply run this container that I just showed you guys. Oop, that's the wrong command. Sorry, guys, here we go. So it's a Docker run command, run it in interactive mode. I'm doing some port forwarding here. By default, Chassis will expose the gRPC server on port 45,000. So I want to port forward that to my local host. And we see that the model spun up right away, and the server is running on port 45,000. That's great. If anybody has ever worked with APIs, you may have heard of the tool Postman. And Postman makes it easy to interact with gRPC models, or APIs rather, and test them out. So what I'll do is show you the 3 remote procedure call APIs that are available within this container. So I spun this up. I'm going to start with the status RPC. And when I invoke this RPC, we get a bunch of metadata returned, things that are all defined by Chassis internally. And if I go back to my terminal here, we see some logs. The model is initialized successfully. Great. That's super easy to use. There's ways to, there's actually a built-in functionality in the Chassis SDK to run this and do this yourself. But what we're using is a gRPC client to interact with the container. Now, what I'd like to do is actually run a sample inference. And to do so, I've got my example message right here. What I'm going to do is go over to this handy dandy base64 encoding tool and copy the base64 encoded version of that 9-digit that I used before. So I'll paste this in here, and I will invoke the run RPC. And in a few seconds, or not even a second, we get the results. This is a limitation working with Postman, is that it doesn't do any of the decoding for you. But if I paste this here, decode, we see the exact same result as we saw in my notebook. And then if I go back to my terminal, we see another log saying, yep, completed the run route in less than a second, right? Or actually 3 milliseconds. So pretty cool and really easy to use and powerful. And in just a few minutes, I went from a Python model to a production container that I could hit via an API. This hasn't finished building yet, but should in a second.
Quick question, Brad.
Sure. Yeah.
When you showed us that Jupyter notebook, there was some sort of a URL that went off to Modzy, right? There was some sort of a API Modzy. How does that? So explain to me a little bit how that works. Is that where the work is being done, or what?
Yeah, great question. So this, yeah, so you wouldn't be able to access this via the URL. It's simply the Chassis service. So Chassis is a Kubernetes service running, and we're hosting it in our cloud and making the publicly hosted service available to anybody. So you're absolutely right. When I execute this publish command, what I'm doing is locally from my notebook, sending this asset, this Chassis model object, to the Chassis service hosted in our AWS cloud, does the processing, does the container building, and then it will push it to the registry associated with the credentials that I've defined.
Gotcha.
Yeah. Okay. Does that make sense?
Yeah, it does. And so that's just a free service. So I guess anyone that uses this should use that URL. It's not really subject to change or anything, right?
Definitely not subject to change. It's on our doc site. Like we promote it. So if you want to use a free version, it's definitely the easiest way to get started. But again, if you wanted to kind of customize this, there's ways to stand it up in your own infrastructure. If you kind of manage different Kubernetes services independently of that.
Gotcha. Makes sense. Thanks.
Yeah, thanks for the question. And as you asked me that question, it looks like the updated model was built. Just to show you guys, it actually does work. We've got version 002 pushed just a couple minutes ago. So it does the same thing as version 1, but again, really easy, really quick to build containers. So that's a really simple example of Chassis. And I think to reemphasize what I said earlier, in just a couple minutes, Python model, container, it's now transportable. I can run it anywhere, which is a good segue into some real life examples of Chassis at work. Before I dive into the examples themselves, I think it's important to talk about why it's so difficult to deploy ML models to edge devices and kind of dive a level deeper of what I talked about earlier. I've had to do this manually where I've taken like a PyTorch model and I work with a couple of different optimizers and deploy a bunch of custom software onto a small device, plus configure the operating system. And if that has a GPU that it requires, right. So the point is it's very cumbersome, manual, and would not recommend it. So some of those specific complexities and considerations we have to make when you do so manually, again, are the device setup, OS installation, system level dependencies, resource constraints. Are you working with an edge, enterprise grade edge server with dozens of CPU cores and hundreds of gigabytes of RAM? Or are you working with a little tiny device like this, right? That has, I think, 2 CPU cores and 8 gigs of RAM. Any external software required for your model to run? How are you going to secure the model on the device or to secure the device itself? And then the model requirements themselves. So by containerizing models with a tool like Chassis, it reduces a lot of these complexities and kind of makes it so that you don't have to even think about a lot of them because we've bundled a lot of that in the container. All you need on the device is an operating system and Docker, and you should be able to run that as well with those API accessible that I mentioned. So again, we've kind of talked exclusively about containers up until this point, and now we're going to kind of move a little bit down the line. And it's important that you have containers. I think it provides a robust foundation, as I mentioned. But when it comes time to scale out these containers to not 1 or 5 devices, but dozens or hundreds of thousands of devices, it's important that you have a solution that's very flexible and very efficient. I like to kind of categorize different devices based on power consumption and network connectivity. And when you think about the near edge, as an example, a MEC server attached to a 5G tower, that telecom providers, use, they have both a lot of power and high network connectivity. So it's typically easier to deploy a model there. But at the far edge, maybe a drone as an example, it's much lower power and certainly less connectivity. And so, it's important that the containers you build can be agnostic to all these different device types across kind of a whole suite of different silicon that we're working with. Which leads me to a concept that we talk about a lot with our customers that's just kind of interesting to talk about, those being edge first design patterns. So I'm not going to go through all these in the interest of time. When I will talk about native edge, but native edge is the idea that you're going to deploy a model to an edge device, and it's going to be doing the inferencing directly on that device. Network local can is similar, but it can process larger loads of data. Edge Cloud is what we like to think of as a broader MLOps solution deployed to a manufacturing plant that may be connected to dozens or hundreds of sensors and can do different types of loads of processing. And then finally, one that we talk about with our customers is remote batch, which is where you can actually send a model to a remote Spark cluster. So instead of transferring large data to from clusters to some cloud processing, the idea that we can send models directly and run those remote batch jobs. So in this design pattern that we will talk about today, some of the examples I'm going to show, it's this idea that now that because we've containerized models, we can manage them, all the containers centrally. We don't have to worry about all the dependencies on a per model basis. Those containers are all accessible via API. And the ability to then remotely deploy these containers to remote edge devices really is pretty beneficial and advantageous. So some examples that I'll show today would be on an NVIDIA Jetson Nano, on a Raspberry Pi, or the little single board computer I keep flashing. And with a architecture like this, there's an added benefit of a telemetry path back and forth between edge device and your central hub that may be installed in the cloud or on-prem, right? So conceptually, this is what that might look like. In practice, there's a couple ways that you could execute something like this. So let's take for an example, you may download a TinyBert model from Hugging Face. We've built dozens of pipelines that will automatically containerize this model with Chassis, and it makes it converts a Hugging Face model into a format that's the same as your PyTorch model or your scikit-learn model. And then if we wanted to deploy this to that remote device, again for the native edge design pattern, there's a couple options here. You could do what I just did. I showed you guys how to download the model with Docker and create your own gRPC client in whatever language you're working with, interact with that container directly. Or you could use different serving platforms out there. Modzy happens to kind of account for a lot of these edge specific needs. And so I'll show you kind of high level what that looks like. But what we provide is the ability to scale this to many devices very, very quickly and easily. So with that, let's get right into some of these edge specific demos that we've built out. Keep in mind that, again, I'm going to show Modzy because some of the mechanics are a little bit easier, but these could all be recreated, totally with custom code on your own, taking advantage of Chassis. So the first sample app that we built is an edge-centric NLP web app, relevant to that slide I showed a couple slides ago. So we downloaded a text classifier from Hugging Face, we containerized it with Chassis, we deployed it to our private model library in Modzy. And then what we did was we deployed that to a Raspberry Pi. So Seth, Justin, I know you know Seth. Seth may or may not be here, but he's got a little lab in his office in Fairfax, Virginia. Oh, Seth did join. And we've got a bunch of fun little demos built in there. But we deployed this text classifier to the Raspberry Pi. And then we built a simple Flask app interface that kind of acts as a chat bot. So I'm going to be streaming that Flask app from my computer here in Philadelphia. And what we're going to do is send data to a model running on Seth's Raspberry Pi. That, if you can see, is he's showing you right now in his little lab right there.
Nice.
So let's do that. So first thing, actually, let me go back here. Within Modzy, so we've got all of our models deployed into a central library. I'll just show you the model that we're going to be working with, this Hugging Face TinyBert model. There's a ton of customization here. I've linked the specific model card. And so we see that this is directly from Hugging Face, again, using some of the transformers code plus Chassis code, super easy to build a container out of it. And then what we can do is go check out a device group we created that allows us to send a model from our central MLOps platform that I mentioned out to a remote device. And we've defined that model here. I'm happy to use an ARM version because Raspberry Pi has an ARM chip. And what we see is a device that's registered with Modzy. Now, how does that actually happen? Well, what we do is we create a device token. And when you run these 3 lines of code on that device, two main things happen. Number one, the device will download any models that you specify as a part of this device group. And so that's the first action. And the second is the device itself is registered with Modzy. This will allow that large scale I mentioned earlier to manage not only models being deployed out to a single device, but hundreds or fleets of devices. So we've got our model here. We see some of the information returned from the device. And we have an easy to use API. Basically, this is a wrapper around that gRPC call that I showed you guys in Postman earlier. Super convenient, easy to use, and makes the application development pretty straightforward. So we've got this, and what I did, as I mentioned, is build a very simple Flask app here. So we've got a Flask app. I've got a Hugging Face model running on a Raspberry Pi, and I've got a little text box here that I can pass some text through. So I'll start with Happy Thursday. We see that the model says that this is a joyful bit of text. I mentioned early on that the weather here is awful and very hot and humid, unlike Minnesota. And we see the model says it's sad, so that it's fun, right? So the point is, this is a fun little app that we can build that takes advantage of a chassis container, again, running on this small form edge device. Really, really easy to use with, as you can see, like extremely low latency. And that's because of the gRPC API that we've exposed through the container. Again, fun little app and prototype to build.
So how does it get through, like, I don't know, firewalls, for lack of a better term, right? I guess he's got a private IP probably, or a...
Yep, that is a great question. And the short answer is, in this case, I have access to that firewall, and
Gotcha.
I send a port forward to my local host. So I basically remotely SSH into that device and port forward it. But what I'm using in this Flask app that I'm running locally is some of that, the Modzy APIs we define that I showed right here. It's basically a wrapper around this to take text, send it to the device, and send it back to my Flask app. So that's definitely something that's a great question, something to consider on a per use case basis, and figure out what that networking looks like, what the guardrails look like, and what your networking and security policies are going to be.
Gotcha.
Cool. Thanks for the question. All right, back to my slides. I have one more app I want to show you guys, or demo rather. And this one could be applied to a manufacturing use case. So also in Seth's office, we have a 3D printer. We printed out a bunch of little spur gears that you'll see in a second. And we manually defected them and put some scratches, broke some teeth off, and put some dents in them. We used those defected parts, snapped a bunch of pictures of them, created a data set, labeled it, trained a custom YOLO model. And then with Chassis, we very quickly containerized that and deployed it into our central Modzy platform. Again, this kind of falls into that first design pattern I talked about of native edge. And from there, we were able to deploy that model out to a Jetson Nano. Now, imagine in a manufacturing plant, you want to automate some quality control or QA processes on a conveyor belt. So what we've done for the purpose of this demo is attach a little web camera to the Jetson Nano. We've got our defect detection model running on that Nano and making real-time predictions on the spinning plate you'll see in Seth's office. And then we built a sample mocked-up dashboard that might resemble something that a floor operator or site engineer might take advantage of to monitor these processes. So again, I will, for being complete, I'll show you the device group. This time it's spear gear defect detection. We've got my Nano device hooked up. And when I open this, we see a few things here. Let me kick off one additional. Sorry, one sec here. What's going on? There we go. All right. Okay, so what's going on here? A lot of things, right? So number one, we've got the main video feed, and this is what the camera attached to the Jetson Nano is taking in. We're passing this feed directly through the model running on the Jetson Nano, making predictions of defects that you see, as the plate is spinning. And what we're doing is we're taking the predictions, we're rendering frame by frame the bounding boxes, and creating a new video or output stream. So we can see kind of a visual of what this looks like from a front-end view. What Seth is looking at right now is this little Jetson Nano running and this little demo that we have, plus kind of the more granular predictions in real time being updated in this table. Now, as I mentioned, this is simply a mocked up version of what a production application might look like, but with containers, with easy to use APIs. I sound like a broken record. It's really easy to build some of these production applications, right? And so that's the point I wanted to get across. It's highly scalable, highly flexible, and customizable, really, to meet whatever use case you might be working with. All right, so a couple of the demos we showed really scratched the surface, I think, of all of the edge AI applications that are out there. We've worked with surveillance, computer vision examples for image and video analytics, text and audio analytics, things like chatbots, human speech analysis, speech recognition, to sensor and IoT analytics, hooking up models to machine data, to sensor data for predictive maintenance. The list goes on and on. And so just wanted to kind of show the art of the possible with the ability to use these flexible and scalable and portable containers alongside some of the really easy to use APIs. Finally, I would be remiss if I didn't throw a little shameless plug in here for Chassis version 2. So everything I showed you is Chassis v1. It's great. You can go use it today. We are actively working on a version 2 of Chassis, which will come with a variety of added benefits. If there's one way to summarize, a theme for Chassis v2, it is, more optimizations. So for us, that is model container size and model container performance from a latency standpoint. So we'll be building in lots of optimizations, taking advantage of some existing tools like Onyx and OpenVINO, TensorRT, some things like that, to integrate all of that into a production container. If you're interested, would ask that you check us out, give us a star, and follow along as we release updates, in the next few months over the course of the summer. So that concludes everything I had. It was great to be here. Thanks again, everybody, for listening. And feel free to reach out. Would love to connect if any of this was interesting and you'd like to chat more.
All right, that was awesome, Brad. Very, very cool. I'm super impressed. The one thing that popped in my head is, like, how long have you guys been working on this? How long has this project been out?
Yeah, that's a good question. Seth, what has it been? Over 2 years since Chassis has been out?
Yeah, just around that time, I think, since we first rolled out the alpha of building these containers, keep adding to it.
Gotcha. And it looks, I mean, it's kind of looking through the source code. It's all written in Python too, right?
Yes. Yep. That's another thing that we'll be changing on slightly in V2. So the plan is to remove as much actual Python in the container as possible, but with the user experience still being in Python. So I'm using some of those optimizers I mentioned to compile Python code into more machine level code with tools like Onyx, and implementing the execution with Rust with some Python bindings, so that we add some acceleration and optimization in there.
Gotcha. Yeah, so you mentioned Rust. I guess you guys are finding better performance with that.
Yes, definitely.
Sure. Well, good. Yeah, if anybody else has any questions, I guess feel free to unmute yourself. Ask them as needed.
It's not like a question, but a discussion, because I'm using a lot of machine learning tools, but based on the Apple ML. And I'm trying to compare what you just presented with recent Apple core model libraries, which is very easy to implement, much simpler than using docs and everything. It's you develop the model, upload it into the library, Apple library of models, and then you can invoke it in my phone, in any computer supporting ML libraries, core ML, which really I can say that it's really simple comparison to what example you give me on this presentation. I can tell you what I can train the model on my Mac, linguistic or visual, upload it in the cloud, and invoke it in my iPhone using almost the same technology with security and everything, with a much simpler way. So what can you say about this?
Yeah, so CoreML is built for the iOS ecosystem. So if you're working specifically with iOS hardware, all of their chipsets and all of the operations are very tightly controlled by Apple. So it creates a really great ecosystem if you're within iOS. But the second you have to get that same model and same code to run on a different chipset, different architecture, running across ARM-based, RISC-V5 or RISC-V chipsets versus AMD and Intel chips, trying to accelerate on all the confusing instruction sets. That's where things really start to go off the rails. And in a lot of production spaces, you don't always have control over where the hardware is going to run. So one of the things that Chassis is trying to provide a solution for is when you have to run machine learning models in a lot of kind of weird places, and oftentimes with really old hardware. So if you've got a 15-year-old server rack somewhere, and that's the only place where you can run your smart cities model, Chassis gives you the tools to basically run wherever.
Yeah, that makes sense. But in my case, I spent about 10 years working with edge processing. So it's a lot of data collected from sensors. In my home, I have about a dozen of sensors, from collecting temperature, movement, and everything, just experimenting with this. And the reason I'm using this Apple platform, because all these different devices, I have one platform which collects this. That's my sensor number one, sensor number two, they're all different. It's a mess of variety of sources, processors, architecture. So it's impossible to use core learning, whatever, machine learning in the various devices. So I need some kind of central server in my edge, inside my edge, in my local home or business, small business, whatever environment. And that's why it was only two platforms, Windows or iPhone, as a central point, collecting data, controlling data, showing the graphs, etc. For the people. So that's why it's technically in reality, in real life, I need a screen to control inside my local environment, and that's why it's not so many, not many varieties. It's Windows or iPhone, or sorry, not iPhone, but Apple.
Yeah, that makes good sense. That I think it's a great solution. One of the other solutions we see solving for the same kind of problem is increased use of MQTT as a kind of binding agent to pull all these different clients together through some, one common way to send and receive information. And that way you can have whatever kinds of clients you want to use for both the interface as well as collecting data from, 1,000 different sensors in different namespaces.
And one more, it's probably last sentence in this discussion. So let's see, I am using a combination of different models. It's not one. Like in my specific home, in the winter in Minnesota, my wife usually, very often forget to close the window after he get a fresh. So I fight with her, but then I put the sensor, which actually sensor outside, sensor inside, and when it's checking it's not machine learning model in traditional way. It's not learning, it's learning my logic. I just compare the temperature. And if it's a winter, it's a temperature below this and that. And it's a JavaScript logic, which I load in a little Raspberry. And Raspberry, again, can talk to the more complicated center, which combine different models and generate result. Because result, it's supposed to be message sent to me through my phone or Windows phone or Android phone. So close the window. it's called. So this is combination of different models, where some of them could be simple JavaScript, some of them could be, you know, statistical learning and language, of course, recognition. Yeah. Thank you.
Yeah, I think you guys have sort of I was going to say, I guess, you know, you're going after a specific problem where people are good at building models, but they don't know actually how to host them in a lot of different ways, right? And you're using Docker as that intermediate platform, and I think it's super powerful to be able to essentially go from a Jupyter notebook to now all of a sudden that's something you can run in the cloud that is scalable through Kubernetes, and then B, push out to devices as well. Are these models, and maybe you like covered this, but I mean, are there commands then to push updated models out, or do you need to deploy a whole new Docker instance? Is that kind of how this works?
When you say deploy like in the example that I gave, like I built version 002, right?
Yeah.
Are you saying, yeah, so today, like that's kind of where Chassis ends. So the way in which you deploy these models out is kind of up to you. But again, if you've integrated this into a registry that you're hosting alongside your other Kubernetes applications, you know, we have folks who have used Chassis to kind of customize the deployment of new versions. Chassis itself doesn't necessarily handle that execution, but something that we've seen people kind of build on top of. That makes sense.
Sure. Okay. Yeah, I don't know if you guys are familiar with Edge Impulse. Is that a platform you guys are familiar with as well? I mean, they have a similar type thing, but their thing is a lot more training in the cloud. And so you guys don't really focus around that. You guys focus more around the operations side of it and maintaining all these devices. And
exactly right. Yeah.
Yeah, they've got a super cool platform, and especially for things like embedded devices where you don't have an operating system and you're just creating these little Arduino packages. Edge Impulse is awesome. They got some really cool stuff. Yeah, ours is a lot more focused on just running the model anywhere. You've got a Docker or a container runtime.
Mm-hmm. So then, how does this then fold back into the Modzy company, I guess, right? The offerings that you guys do, because you guys didn't really talk a whole lot about that. So maybe you could just talk about that briefly here for a second. Plug yourself a little bit.
Yeah. So, you know, the way we look at it, you got to start with good models to build functional machine learning powered ecosystems and powered applications. So we built Chassis as a way to help all of our customers more quickly take a bunch of Python code and turn it into something that you can deploy in production. The next step of that is running, orchestrating, monitoring those models in the real world, connecting them to other systems, tying them to different databases, S3 ecosystems. So what we provide with Modzy is a way to run those models on your hardware of choice, from fleet of 1,000 edge devices to scaled up cloud clusters, a whole set of APIs around those models to interact with them. So it becomes a line of code to connect them to an S3 bucket, a database, your Snowflake instance, and then a whole set of monitoring tools, from drift detection to explainability to inference monitoring speeds, cluster utilization, and then all the security that comes with who's allowed to use certain models, how many times per day can they call that model, who has approval workflows so that those models can be run on production workloads versus just testing and research and development clusters. It's all the monitoring, management, kind of orchestration tools that you'd want to use, typically in a larger organization where that kind of governance is a requirement.
Gotcha. Yeah, so really moving it into the enterprise environment.
That's right.
Seems where you guys sit. Cool. Well, actually, I think I was just going to take a look back with regards to when our conversation was. I was going to drop a link here in the chat here. Greetings. With regards to letting people know about our podcast that we did. So I'll make sure I drop that in here. Is there any other questions that people have for the guys here? All right. Well, I think we might be done for the night. Seth, Brad, I appreciate your time. This was really, really awesome. I think the tool that you guys have created, I think is definitely fills a niche with people that are, they don't really know, they're more on the data science side. They've got a model, they know how to build that stuff, but they don't know actually how to at least get it out, either on a device or into the cloud and be able to, utilize it in more than just their desktop, I guess. So, Jim, you got a quick question? I see your hand up.
I do. So, nice product. Nice to see you guys working. I have an associate in Philadelphia. So can I ask what kind of clients are using your product? Who are you selling the product to?
So we generally try to avoid specific names, but I can give you enough info to probably figure it out intuitively. The primary areas where we're selling our product are in life sciences and life science research, energy and utilities, and manufacturing. So we worked with some customers that build really heavy machinery. A lot of their business is selling to the Department of Defense, various vehicles. We're selling to one of the largest telco providers in the world. We also have customers in life sciences that do production of medical devices, and they're using machine learning for both a lot of IT and operational technology use cases, as well as some different public sector customers. So it really runs the gamut, but by and large, I guess more focused on what you might think of as an industrial and certainly B2B type end customer than business to consumer type customers.
And what about relationships? You happen to have a nice plethora of universities and college there. Are any of them working with you?
Yeah, we've been in touch with a few universities. I think we had some conversations with McGill and Waterloo. I've been up to, I went to MIT for my undergrad, and we're part of the MIT Startup Exchange. So we've been up there a number of times and hang out in Boston a fair amount. I think those are the main universities so far that we've worked with, but we're very eager and interested in working with anyone in the space. And certainly part of our contributions to the open source community, we hope folks find value in. So
great, thank you.
Mm-hmm.
All right, guys. Well, thanks again for all the information and for presenting your product and the open source work that you guys do. I think it's awesome.
Thank you. Yeah, great meeting all you and appreciate the discussion.
Yeah,
all right, keep in touch.
Have a great week.
Talk to you guys soon. Yep.
Thank you.
Thanks.